All right, welcome back to Unit 11. Today we're going to do, this is day 3, we're going to distinguish between strong and weak acids and bases and use our H+ to calculate the pH of a solution. All right, so the first thing, your vocabulary reminder, dissociation is going to be a general process in which molecules split up or decompose into their ions. So salts, acids, or bases. Whenever you put them in water, they'll dissociate and turn into electrolytes, like NaCl. Oh, it's down here already. NaCl will dissociate into sodium cation and a negative chlorine anion. If you don't remember the difference between those two, cation has a little T right here, which is positive. So you can always remember that cations are positive, and anion has a line through the A, so that's my negative sign that's over here in chlorine. All right, so between strong versus weak acids and bases are classified as strong or weak based on to the degree which they dissociate in water. All right, so strong acids and bases will completely dissociate into ions in aqueous solutions, and weak acids and bases will only partially dissociate into ions. Okay, so over here, this example, see how we have these compounds that separate completely into their own elements. Every single compound separates completely. This is going to be a strong acid or base. And on this side, we have a compound that only separates once. Okay, it doesn't separate every single compound, so this is going to be a weak acid or base. Okay, so this one is an example of a strong one. See how we completely dissociate into our cation and anion, and over here we kind of dissociate into our choices. We mostly stay as our original one. Okay. All right, so sometimes people can confuse the concepts between concentration and strength. Okay. The words concentrated and dilute indicate how much of an acid or a base is dissolved in a solution. So these terms refer to the number of moles of the acid or base in a given volume, which is our molarity or concentration. Okay, molarity and concentration are the same. Okay. The words strong and weak refer to the extent of dissociation of an acid or base into ions. That was our original definition. Okay, so working with concentrated acids can be very dangerous. So when diluting an acid, we always want to remember you always add acid to the water slowly while stirring. I used to work in a lab, and I have a lab coat that's full of bleached areas where hydrochloric acid just ate up my jacket. Okay, so if we're looking at these two lights, and they're put inside a solution, can we tell which one is a stronger acid? So you can see this light is obviously brighter than this one. So we're going to say that this strong acid had a complete dissociation, which means it created a lot of ions. Okay, by creating those ions, it made it an electrolyte. All right, and the weak acid only had a partial dissociation, which means it created fewer ions. Okay, so more ions created a better electrolyte, fewer ions created a poorer electrolyte. So this one is our stronger one. Okay, so let's circle one word, or I'm going to highlight in each pair. So hydrochloric acid is a strong acid. It will completely dissociate because it's a strong acid, producing many hydrogen ions, making it a very strong electrolyte. Okay, we said it was strong, it has a lot of ions, and it completely dissociated. Okay, aluminum hydroxide is a weak base, so it'll only partially dissociate, producing few hydroxide ions, making it a very weak electrolyte. Okay, remember acids are made with hydrogen, bases are made with hydroxide. Okay, that's how I knew whether it would be hydrogen or hydroxide. Okay, so we're going to place brackets around a value to indicate the concentration or molarity of our solution. Okay, so whenever you see H+, you should always read it as concentration of our hydrogen ion. Okay, so I want you to make this note in your notes. So if you see H+ and or H3O+, that's what we're going to read as my concentration of H+. Okay, so not just H+, but H3O+ are going to be our concentration of H. Make that note, pause this and make that note in your notes. Okay, this is because H+ in a solution is typically such a small number, we use a pH scale to help us relate acids and bases. Okay, our pH scale indicates the H+ ion concentration in a solution. So the pH scale will range from 0 to 14. All right, and it looks like this. I'm pretty sure you've seen it before somewhere. All right, so this is our pH scale. We're going to distinguish the differences between 0 to 3, 4 to 6, 7, 8 to 10, and 11 to 14. Okay, so the first thing we want to make is 7 is always going to be neutral. That's where we are happy. Okay. Acids, our pH scale is below 7, and it produces the most H+ ions. Okay, so over here we have the most H+ ions. And our pH at 7 makes equal amounts of H+ and OH. And then bases will have a pH that's higher than 7 over here and produce the least amount of H+ ions. Okay, so acids have a pH below 7, neutral is at 7, bases are higher than 7. All right, so some examples. I want you to go ahead and write these above your little numbers up here in these spots. Okay, so a pH of 2 would be like your stomach acid, 3 is lemon juice, vinegar, 4 would be soda water, 5 is black coffee and bananas, 5.6 is normal rainfall, and 7 is going to be your pure water. All right, and then 8 would be like a raw egg, 9 is like baking soda, 10 is your bar soap, ammonia would be 12, and 14, as basic as it gets, is your lye or oven cleaner. Okay, so the pH of a solution is the negative logarithm, negative log, this is a button that's on your calculator, of the H+ concentration. The pH may be represented mathematically using this equation. Looks like this. Good stuff. We love math. In pure water or in a neutral solution, H+ equals 1 times 10 to the negative 7th power m, and I'm looking at that 7. My pH is going to be 7. Okay, we want to look at our exponent. Okay, we express H+ in scientific notation to make it easier to calculate pH. So for example, we're going to rewrite 0.001 m as 10 to the negative 3 molarity. Okay, if you don't know how we got this, all we did was we took our decimal, moved it this way 3 times, turned it into 1.0 times 10, and we would move 3 spots to the right, so it's negative 3 m. That's my scientific notation. All right, so my pH for this solution is going to be 3. All right, so pH is equal to x when 1 times 10 to the negative x is whenever it's 1 times 10 to the negative x. Okay, if we have a different number other than 1 there, then it won't be negative x. We have to do something else to it. All right, so it's easy to find our pH whenever our coefficient is 1. The pH of the solution equals the exponent with the sign change from negative to positive. Okay, so pH is x whenever 1 times 10 to the negative x. Whenever it's 1 times 10 to the negative x. Sorry, can't speak. All right, so for example, we have H+ is equal to 1, we're good, times 10 to the negative 2. So I'm going to take that negative 2, turn it into a positive, and that's going to say my pH is 2. All right, so if the coefficient is other than 1, you would need to use a calculator with a log function to calculate pH. So we won't be doing this in class. We're always going to use a coefficient of 1, but in case you ever study chemistry later, just know it does get harder. Isn't that exciting? All right, so let's look at our 3 examples. We have 1 times 10 to the negative 3, 1 times 10 to the negative 3, and 1 times 10 to the negative 3. All right, that's all going to be the same thing. So my pH for each one of those is 3. And we can find that right here. That's going to be an acid. Okay. Okay. This just says that molarity of HNO3 is also H+. Okay. And we will use these interchangeably. All right, so let's look at this one, our last example. We have 10 to the 1 all the way down, so we're good. We don't have to do anything in our calculator. We have, I'm going to use a highlighter actually. We have negative 6 here, so that's going to be a pH of 6. And we have, at 7 we're neutral, above 7 is going to be basic, below 7 is going to be acidic. Okay, so this is 6, it's below 7, so this is going to be acidic. Next one, we've got negative 10, change it into a positive, so it's going to be 10, and that's above 7, so it's going to be basic. Next one, we have negative 8, change that into a positive, so it's going to be 8. That's above 7, so this is basic again. Next one is 2, that's, negative 2. We're going to change that into a positive, so it's going to be positive 2. And that's below 7, so it's going to be acidic. And then the last one, we've got 13. Ooh, that's pretty basic. So it's going to change into a positive 13, and that's way up there, so it's going to be basic. All right, thank you for joining me. Make sure you go watch your homework video. Good luck.